Okay, so, welcome to class 2. I start with, we'll be discussing thermodynamics, a brief overview of thermodynamics today. But I start with the picture of James Clerk Maxwell, who not only developed electromagnetism, or we know about the Maxwell equations of electromagnetism, but also had a crucial role in development of kinetic theory, and you might have heard of the Maxwell-Boltzmann equation, the distribution of speeds and the velocity, the probability distribution of speeds of velocity at different temperatures. So he was basically worked in Edinburgh, Scotland, and mostly the pictures I've been showing you are of extremely old men, and I found this is the more common picture of Maxwell. But this is how he looked when he was young, when he was a college student or something like that. And I just thought that, I mean, we hear about these people, let's give some pictures. The other thing I just might mention that I read up in Resnick and Halliday, there's a footnote that many of the people who worked and established the first law of thermodynamics, I mean, finally it was written down by are expressed in the final form by Clausius, but there were many others, including Sadi Carnot, who had were working on this work, force into displacement, because work and energy, right? Heat conversion. And many of them were very young people. That's a side story, but I thought just to give some story. But today we'll be discussing a brief overview of thermodynamics, which deals with transformation of heat. You heat a gas, and such that the gas expands and pushes some piston, and you get mechanical work out of it. So that's why thermodynamics was developed, right? Because you want to make a push something or pull something, like raising water from a well. So that's work done, force into displacement, or push uh, maybe a rail train or anything, and that's mechanical work, and that's uh, what thermodynamics deals with. I mean, that's how it developed, rather. So what I'm going to discuss today, a brief overview of thermodynamics is there in the book of Gerson Huang. The entire book of Enrico Fermi is a wonderful treatise on thermodynamics, but it's a very thin book. And there's also a brief description, overview of thermodynamics in Meren Kardar. Of course, you have the Zemansky, but that's an entire book devoted to thermodynamics. So this is a brief overview. So whatever I'm writing down is basically taken from these three books, so one or the other. So what is a thermodynamic system? It's a macroscopic system defined by measurable macroscopic quantities associated with the system. And if you're talking about an ideal gas, then the quantities measurable mean values are pressure, volume, temperature, right? And if I'm talking about a magnetic system, then maybe H, the magnetic field by which you control the magnetization of the system. Here, I mean, and that's an intrinsic quantity. Here, pressure is some, if you have some volume of a gas at a certain temperature, pressure is something which you can change to change the volume, or temperature is something you can change to change the volume of the system. All right. So a thermodynamic state, a macroscopic thermodynamic state is defined when we can specify all the thermodynamic parameters for the description of the system. And you also have the equation of state, which states that all of these quantities are not independent of each other. So if you change temperature, then pressure and volume will change, and so on and so forth. If you change magnetization or temperature, or rather if you change magnetic field, external magnetic field in which a magnetic substance is kept, at a certain temperature, then the magnetization can change. If you remove the external magnetic field, if you remove the B field, you just have a magnetized sample iron at a certain temperature. By changing the temperature, you can change the effective magnetization of the system. And those can be initially empirically obtained. Right, and that is within the scope of thermodynamics. Whereas if you specify the microscopic interactions, the microscopic degrees of freedom using statistical mechanics, you can derive the equation of state. And okay, while you derive it, you of course want to match it. So what is the input? There will be microscopic degrees of freedom. If you're talking about a magnetic sample, then you will be talking about how many magnetic moments or spins are sitting at different points in the lattice, and you will be also specifying the interaction. Now, how do you know the interaction a priori? You don't. So you write down a model Hamiltonian, and then you calculate using methods of statistical mechanics the equation of state, right? And that is known empirically. And if you're calculated using methods of statistical mechanics, if you get your thermodynamic equation of state, which is obtained empirically, suppose Curie's law or Curie-Weiss law, if you have heard of them. If not, we'll be covering it, never mind. So how does magnetization change as a function of temperature? If you can calculate that, and that matches quantitatively with your calculation, then you can say that, oh, all that I used is this Hamiltonian, these degrees of freedom. Then maybe this Hamiltonian is the right microscopic description of the system, whose properties we can measure macroscopically and control different quantities macroscopically. So that's the scope of statistical mechanics, and that's how you connect with thermodynamics. But even within thermodynamics, empirically, by observations by Charles' law and Boyle's law and whatever that gas law, different thermodynamic parameters are related, and that statement, that relation between different thermodynamic parameters which describe the macroscopic system, the relation between these thermodynamic parameters is called the equation of state. So as per Kardar, the book by Meher and Kardar, thermodynamics is the phenomenological, right? You observe and then you write down an equation. The phenomenological description of the properties of a macroscopic system in thermal equilibrium. Now we're going to talk about what is thermal equilibrium, right? But before that, the phenomenological description, what does it mean? Let's, before going on to what is thermal equilibrium, by measurement, by suitable measurement of the pressure, the volume, and the temperature of a real gas, of an interacting gas, say, right? You lower the temperature so that it's not an ideal gas anymore. Interactions between molecules start to play a role. And then you have the van der Waals equation of motion, that if you change pressure slowly, volume will change or temperature will change, right? So this is a phenomenological description of the properties of matter, right? Now we keep talking about this ideal gas, so I wanted to give examples away from the ideal gas. And if you have a Curie paramagnet, not a, right, then by suitable measurement, you can figure out that the magnetization of the sample increases linearly if you have an external magnetic field. Well, magnetization for a paramagnet, you'll observe some magnetization only if you apply an external field. It's not a ferromagnet that it will have show spontaneous magnetization, like iron. It shows spontaneous magnetization even if it's kept at room. Right? But a paramagnet, there are quantities which have magnetic moments, and they align themselves when you apply a magnetic field. But KBT, temperature, higher temperature, also leads to fluctuations. Right? In thermodynamics, we typically don't talk about fluctuations, but in StatMech we will, as a consequence of which it decreases the ordering. Now, this concept of fluctuations comes from StatMech, but even without that, empirically, you can have this phenomenologically, you can have this relation between magnetization, number of magnetic moments, uh, the value of the magnetic moment of each component of the paramagnet, B and KBT. Right, so that's another equation of state. And just for the heck of it, I have written down another uh, equation of state. Now, this is Hooke's law, but for rubber. All right. And here it says that, well, if you have to stretch if you want to stretch a piece of rubber, then the force applied to stretch it by delta L, that's linearly proportional, of course. That's what Hooke's law is. But interestingly, what here you see is that K0, so this is some constant, and K1 into T. So the proportionality constant itself is a function of temperature. And the spring constant, if you like, increases with temperature. So at a higher temperature, you will have to give higher forces to have the same deformation, right? So this again can be derived microscopically, and it will be done in the soft matter course. But I want to stress upon you that this Hooke's law for rubber is very different from standard crystalline materials. So if you increase the temperature of say some crystalline solid, then actually the system becomes softer. There are more phonons, there are more vibrations, and you need less force to increase, to deform it by a certain L. Yeah. But here rubber is behaving very differently. Here with increasing temperature, the spring constant or the Young's modulus or the elastic constant is actually increasing with temperature. And the reason is that the origin of rubber elasticity is very different physics-wise from that of a standard crystalline solid, where it is energy dominated, but here the elasticity, the origin of the Young's modulus or the elastic modulus is entropic origin. Uh, so, so, so that's a slight diversion. I just told you something interesting about what entropy can do. It can increase elastic constants. But again, the point to note is this equation is a phenomenological description of the properties of macroscopic systems. It is seen that the elastic constant actually increases as a function of temperature. For rubber-like material, it decreases for other materials, and this is a phenomenological description. But of course, how these relations arise from more microscopic origins will be the scope of statistical mechanics. But at the moment, I want to note you to note that this is like an equation of state beyond your PV equal to nRT, right? Because that you must have seen since your class 11 and 12 and so on. Okay, so the next point is thermodynamics, the phenomenological description of properties of macroscopic system in thermal equilibrium. Now let's focus on the meaning of the word thermal equilibrium. So in one sentence, thermal equilibrium, a system or is in thermal equilibrium. Usually we talk about its properties are independent of time. All parts of the system are defined by the same thermodynamic parameters. So if it's uniform across the system. More importantly, the more general way of saying this is there should not be any flux or any current in the system. By current, I don't mean electric current. It can be there should be no electric current, there should be no particle current, there should be no momentum or energy current in the system. So if their properties, if there is some quantity which is flowing from one part of the system to the other, then that is system is not in equilibrium. So there should be no flux, and all parts of the system must be defined by the same thermodynamic parameters. So why no flux? Just let me give you an example. Uh, so you can have, of course, mechanical equilibrium where different parts of the system are either at rest or moving so slowly that kinetic energy can be neglected. So basically, nothing is pushing each other. So that the mechanical equilibrium, all different parts of the system are in rest. Chemically homogeneous mixture is in chemical equilibrium. On the other hand, you have suppose more dust particles distributed in a liquid. On the other end, you have pure liquid. Then the dust particles will move, or some chemicals will move from a region of high concentration to low concentration, and then you have a particle current, right? A particle current of dust particles moving from one region to the other, and that is not equilibrium, right? There is diffusion of particles. Only once the entire liquid, say, becomes homogeneous, will you call it chemical equilibrium. And what is thermal equilibrium? Now, suppose you have a metallic bar on one end, say at x equal to 0, you have a temperature T2, you just place this bar at temperature T2 and the other end of the bar is maintained at temperature T1. Then, of course, initially this entire, initially suppose the entire block of metal was at temperature T1, then soon after you put this end in contact with T2, the temperature here will rise, T2, but this will be maintained at temperature T1. But gradually, more and more heat will be absorbed from this end, where I have assumed that T2 is greater than T1, and there will be flux of energy, right? There will be heat absorbed, and that current, there will be a heat current, so that heat is transferred. So energy is in motion, it is transferred from this end to the other. And you might have heard or read through Fourier's law of conductivity that finally it will reach a steady state, right? So that this end of it is in temperature T2, this end is in temperature T1, and there will be a linear temperature gradient across the block, right? But that is steady state and not in equilibrium. Different parts of the system are not in, cannot be described by the same values of parameter temperature. Here it is T2 and here it is T1. Moreover, there's a flux of energy from this end to this end. So there's a current, there's a heat current. There is some net flux of heat from this part to this part. So this system is in steady state. Its properties are not changing as a function of time, but yet the system is not in equilibrium. Right? This is a system in steady state. So you really, statistical mechanics or equilibrium statistical physics is what we will be discussing in this course. That will essentially be talking about systems which have reached equilibrium, right? Which has reached equilibrium, and these equation of states and so on and so forth, they describe the state or the properties of the macroscopic system after they have reached equilibrium. How do you reach equilibrium? You might learn some of it in StatMech 2, but definitely not in this course, right? Okay. So basically what you are saying that so even if a system is not in equilibrium and if it is not driven, if there is not this constant flux of energy, a system will reach its equilibrium even if you perturb temperature, magnetic field, pressure to reach equilibrium. And once it reaches equilibrium, it can be it will follow its equation of state. Sorry. Okay. So you can have thermodynamic transformation. You can change the state or the thermodynamic parameters such that the properties, the other properties of the system changes as per the equation of state. And you can have quasi-static changes in the properties. So you change the pressure quasi-statically, which means very little by little, such that each step, as you change from P1 to P2, you can define it as it's nearly in equilibrium. So P1 will go to P1 dash, will go to P1 double dash, will go to P1 triple dash. And at each state, the system is in equilibrium. There is uniform pressure all over, right? There are no currents. Currents die down very quickly. And I mean, as soon as you change it, and at each point, you can define, suppose it's thermodynamic parameters. You might also change it in a sudden manner, so that you suddenly change P1 to P2. And in that case, there will be non-uniform density, non-uniform pressure. But then the particles of gas, if you're talking about gas, they will basically diffuse, they will collide with each other and gradually reach equilibrium as per Boltzmann transport equation, right? And then again, your PV equal to nRT will hold, assuming an ideal gas. Now, just if you have quasi-static changes, where the system is always approximately in equilibrium, it does not guarantee reversible transformation. If you go back from P1 dash to P1, the process could be reversible or could be irreversible, especially if there is loss or dissipation in energy, as the suppose you're changing P1 to P2 by pushing a piston, in a jar of, so basically suppose there's a jar of glass and there's a piston on top and you're pushing it, so that the pressure increases, say. But if the piston does work or there's some dissipation, there's some friction of the piston with the walls of the jar, then some heat will be permanently lost. So even if you put it back from P1 to P2, or whatever, P1 dash to P1, it will be irreversible, right? So you can have free expansion of gas by successive infinitesimal increase of volume elements, right? And in that case, and if there is no friction and no energy loss, then if external conditions are reversed, the transformation and the state of the system is reversed. But it's not necessarily, not all quasi-static transformations are irreversible, right? Furthermore, transformations can be isothermal, adiabatic, or isochoric. So isothermal changes are those changes where the temperature of the system doesn't change, only pressure and volume changes. Adiabatic are where there's no energy exchange with the environment, that's the total energy of the system remains fixed. And isochoric is no volume change for gases. And for gases, if there's no volume change, there is no basically F dot dx. If the volume remains constant, that by default means that no work is done because the piston is not moving into the jar or out of the jar, so there's no work done, right? So it by default means PdV equal to 0, right? And PdV is work done. What is work done? It's F into dx, right? And PdV can be written as force into area, and dV is area into dl, right? So area into dl, the area cancels, so you get force into dx. So the units match actually, right? So in general, while talking about statistical mechanics, or I mean, so we're discussing thermodynamics so that we can go towards StatMech, right? So when you're talking about an ideal gas, we will talk about pressure into dV as work done, right? When you're talking about a rubber, and you're giving some displacement, F dot dx will be the work done. If you are having a different thermodynamic system, a liquid runs in surface tension, which is basically force per unit length, and then the corresponding generalized force will be this quantity, and displacement will be change in area. Right? And again, you will have force into D. That will be the work done. So what is heat? So heat, I already told, is energy in transport when it is changing in flow. Energy in flow is heat, but the right proper technical thermodynamics definition is heat is what is whatever is absorbed by the system if its temperature changes while no work is done. So there's no work, then temperature changes. So something is absorbed, some some energy is absorbed, and that's heat energy in transfer, right? When energy is transferred, the potential interaction, the interaction potential between the particles remains the same, but the particles might rearrange themselves differently. So part of it goes into kinetic energy, equipartition theorem, right? And because which the particles might rearrange themselves and the total internal energy of the system can change, right? Absorption of heat without work done is going to change its internal energy. Moreover, this is change in heat delta Q. Um, can be written, you might already know this, heat capacity to dt. The heat capacity is per unit mass. Um, so how much of heat is absorbed to change a uh, unit of temperature, right? And if you write it per unit mass or per unit mole, then you call it the specific heat capacity, the molar specific heat capacity, and so on and so forth. So this is just standard, quickly just going over. So what is the zeroth law? So why do you need the zeroth law? So you might already know that the zeroth law is that two systems A and B, if they are separately in equilibrium with a third system C, then A and B are in equilibrium with each other. Okay, so this is the statement of it, but let me discuss why we need the zeroth law at all. So the point is that, you talk about something is hot and cold, and well, you can put something in a hot water and you'll feel hot, but then that's not a definition of how hot it is or how cold it is. The way you measure quantitatively how hot or cold something is by measuring this abstract concept called the temperature, thermodynamic abstract. Now you can't directly measure temperature, or you don't actually, right? What you do is put in a thermometer. Does thermometer measure temperature? Yes, it does. But what changes? What changes in a thermometer is essentially the length of the fluid column. If you're talking about a mercury thermometer, right? I don't know whether you have seen only the digital thermometer, but even if it's a digital, finally, if it absorbs heat, right? Then either some resistivity or some conductivity of some diode or some material, a thermocouple is going to change, and the amount of current induced in the thermocouple is what you're going to finally measure. So again, you are not directly measuring temperature. You're not saying, oh, so you're either measuring a current or you're measuring some change in length of a mercury column, and that's how you're measuring your temperature. Now, now to say, now suppose you have two different objects, right? And it shows the same temperature. It also assumes that both A and B, these two objects, separately in equilibrium with a third system, suppose the thermometer. If this A and B are separately in equilibrium with a third system, C, which is the thermometer, then they are going to have the same temperature, and A and B are in equilibrium with each other. So they have to be in equilibrium with each other to be maintained at the same temperature in some sense, right? And so that's the importance of the zeroth law. Now, 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 different people can come up with different mercury columns in a mercury thermometer, and say that if the mercury expands by this much, this is the temperature, right? And another person comes with another thermometer and says, oh, I will call this particular temperature to be, somebody says 75 and somebody says 70. Or even suppose you fix the boiling point of water in ideal gas conditions and so on and so forth, not ideal gas conditions, whatever, at standard temperature and pressure, at standard pressure, non-atmospheric pressure. You might say it is 100 as per Celsius, and as per Fahrenheit, it is 180, right? So one needs a standard method so that different people across different parts of the world, if they measure the same thing, if they measure the boiling point of water at 1 atmospheric pressure, they should get the same value. And the way this was decided at some point of time in the history, I don't remember, is they use the idealized gas, which means gas which is pretty quite high away, very far away from its uh, gas to liquid transition, where PV equal to nRT is valid, because at lower temperatures, you are going to get your van der Waals equation, right? It might liquefy. So once you are far away from that, where PV equal to nRT, the gas is behaving and obeying the law of PV equal to nRT. It is not going to obey all the time. It is not going to obey once you are close to its liquid point where it becomes liquid. But if you are far away, where PV equal to nRT is valid, there you can use the properties of the ideal gas to figure out to figure out uh, or to set a temperature scale. Okay, and of course you have seen PV by n equal to constant kBT or nRT and so on and so forth. R, what is R? R was 8.32 for 1 mole of a gas, and well, R is 8.32 and Kb is actually R by Na. So this is written wrong. So R is 8.32, the right units. And Kb is R by Na. That's what I wanted to write here. So the way you define a temperature scale, which is unique, right? What you take is 1 mole of an ideal dilute non-interacting gas. Once you fix it, you take just 1 mole of it and 22.4 liters if you like, and take that amount of gas, and basically you measure P and V, and it will have a certain value when water is boiling at 1 atmospheric pressure, right? So let's call that RTH, RT, yeah, because you don't know, you're trying to set up a temperature scale. Now you take the same amount of and look at it at water freezing. Right? Water freezing, suppose you still maintain 1 atmosphere, so the volume will adjust itself so that P into V has a certain different value, and let's call that RTL, right? Now, so RTH and RTL, so these are defined, and divide this into 100 divisions, which is basically like centigrade or Kelvin, right? So first of all, you set the division scale, but you could also call it, I mean, so you have some value here and some value here, but it is undetermined by a certain constant, right? I mean, you need something else. So if you take 1 mole of gas, pressure 0.06 atmosphere, and let the volume adjust itself so that you reach the triple point of water. So triple point is the point where solid, liquid, and gas coexist, and that's a unique point. You need to satisfy all these three conditions. So once you reach the triple point of water, whatever is the value of PV, okay, now if you took R to be fixed here, T will automatically come out to V, or rather you have some value of this, divide by R, and that will come out to be 273. So if you had 1 mole of gas, you were at the triple point, you know what the pressure is, right? The volume will adjust itself to some value, and you take PV by R, and it will come out to be 273. Now, if you fix that arbitrary constant, then so basically call the triple point of water to be 273.16 at 0.006 atmosphere. Unless you adjusted the pressure as well, you wouldn't have reached the triple point. That's a unique point, right? For 1 mole of gas. So that comes out to be 273.16. Now, once you fix that, that's a unit, then you check how far away is it, right? So 273.16 is just above the now you take it back to 1 atmosphere and check what the temperature is, and you will find this point to be 273 and this point to be 373, right? And if you draw this line back, you will see that pressure goes to 0 at minus 273.16 degree. Yeah, 273.16 degree minus, I mean, in terms of centigrade. So basically, the temperature at which pressure goes to 0, assuming this is a straight line. Now, this is an assumption. Of course, the gas, if you lower its temperature, it's going to become a liquid. So, but you are doing this experiment in ideal gas conditions, right? Then you set your temperature scale, and any other thermometer, any other mercury thermometer or thermocouple thermometer, you by which you can go to low temperatures, and some other thermometer you can go to high temperatures, right? And that you calibrate against this ideal gas temperature. You basically look at what is the length of the mercury column at the freezing point of water, what is the length of the mercury column at the boiling point of water, call that 273 and 373, and there should be 100 divisions. That's how you set up the scale, right? And moreover, I mean, you don't just call it 250 or something, because using the triple point of water, you fix that the triple point of water is 273.16 temperature, right? So that's the triple point of water, whereas the freezing point is 273, right? Or yeah, one has to check it up. I'll just check it a bit in the class. So the temperature of any other system can then be defined, assuming you have an ideal gas. You take 1 mole of that gas, uh, put it in thermal equilibrium with whatever other system whose temperature you want to measure, measure the value of P of V. You know what is the value of P and V for 1 mole of gas, the triple point of water, 273.16, assuming the ideal gas. And that will be the temperature of your system. And that's called the Kelvin scale. Right? So that's the Kelvin scale. That's how you define its the zero temperature, right? By extrapolating this line to where the pressure goes to zero, that's T equal to zero, where you have set the scale, right? And this is after Lord Kelvin. He was initially named, his birth name was William Thomson, but later he was, I don't know, knighted or whatever, and he became Lord Kelvin. He was born in Ireland and taught in Glasgow, Scotland. Okay, so that's the end of the second class. So I want to stop recording.